Our theme tonight is, oh, the weather outside is frightful, and it is, so it's well timed. So thank you very much for being here on this night. We actually wondered, with an event so close to the Christmas break, and as it turns out this evening on an evening with not great weather, whether we'd have as many people as we have on previous evenings. So it's good to see such a crowd here. The future of human civilization will be largely determined by our changing climate, our growing population, and our need for resources. Climate change isn't really about the planet so much as about people and their habitat, or at least our focus on it, usually when we talk about it. Not about the planet, but about us and our habitat and the economic, social, and political adaptations that are needed in order to respond to the impacts of climate change. The trailblazers here this evening represent the area from our strategic planning framework related to sustainable prairie and northern communities, and the university's leadership and expertise in the area of climate change research. Each of my colleagues will speak for around 5 to 7 minutes and comment on this discussion theme. They'll be using some visual images that will be on the overhead screen to illustrate some of their points. And then we'll have a discussion from the floor, give you an opportunity to ask questions or make comments. The room is full. On other evenings, many people have wanted to participate, so I'm going to ask you please to keep your interventions brief, state your question, and let the panel respond to it. There will be wireless microphones circulating through the room, and I'll moderate the discussion as we go through that. We asked you to come from 7 to 8:30, so we'll be done by 8:30. And just a few minutes before that, I will ask Digvir Jayas, Vice President Research, to provide a short summation of the key points that are made this evening. So, to business. Let me tell you about our first speaker. Dr. David Barber holds a Canada Research Chair in Arctic Systems Science and is Director of the Centre for Earth Observation Science at the Clayton H. Riddell Faculty of Environment, Earth and Resources. He conducts field and theoretical geographic research that expands scientific knowledge pertaining to Arctic climate change. His work involves understanding climate processes affecting sea ice and the consequences of change in sea ice timing and cover. He's the lead investigator of several large-scale Canadian-led international research programs that utilize the Canadian research icebreaker Amundsen. David?
Thank you. That little spinning globe that's over on your right is what my group studies. We're interested in how the Earth functions. We're interested in its climate system and how it is behaving as our habitat. So we have a whole bunch of us now on the planet, and we all make use of this Earth as our habitat. We have to think of it that way, and I usually put things in that context. The reason I put the globe up there is I want you to draw your attention to that blue limb that you see around the planet. That's our atmosphere. And if you talk to astronauts that go to the space station or are out in shuttle missions or on the way to the moon, this is the key feature that they see about our Earth. They see this blue limb. And that is the atmosphere that we breathe. And that is the atmosphere that sustains life on the planet as we know it. If we go to our nearest neighbors, Mars and Venus, that blue limb is a much different looking beast. So when you go to Mars, it's kind of non-existent. There is not really a gaseous atmosphere on Mars as we know it here. It's much less dense than the one we have. If you go to Venus, it's much more dense. And so the greenhouse effect of those three planets are much different. Venus has a surface temperature which is very, very hot, not very suitable to us carbon-based life forms to live there. If you go to Mars, it's very, very cold. Again, not particularly conducive for us to be there. I was very excited to see that NASA has launched the next Mars mission, which departed about a week ago and is on its way to Mars now, and will look for the existence of past life on Mars, because we think Mars at one time did have an atmosphere and did have water on it that could sustain life. So there's some very exciting things going on. Now, if we try to look outside our own solar system, we also have some exciting news that Kepler just found another Earth-like planet called Kepler 22b. That happened also about a week ago. And they think this is a habitable planet, but it is 600 million light years from us. So that's a little bit far to go in my Toyota Prius, so I guess I won't be taking up that one anytime quick. To study that system, to study this Earth, is a very complex thing. So the Earth's climate system is very complex, and we know it is very complex. It has driven a lot of things on our planet. For instance, the computer revolution that we take advantage of right now, the early days of that and the development of supercomputers was really driven by the need to model that complex system. And we're still in that situation today. The main things we use to study the Earth's climate are process studies. So we have observational systems all around the planet. You're familiar with climate reporting stations. We have them here in Winnipeg and at the airport, and they're all around the planet. They've been around for only about 150 years. So it's not a very long record to use these observational stations. We have instruments that we can put out in the field, and we can measure the different fluxes that are associated with energy and mass and these kinds of things. We can use satellites to study the surface of the planet. We have very high-resolution satellites now that have been in space for about 30 years. So again, the record is very short for the kind of things we can do with satellite systems. We also have paleoclimate records. Paleoclimate records are things that take us back in time and tell us what the climate system looked like on Earth by studying the way things were deposited on the bottom of oceans, or the way ice was deposited on glaciers, or the way trees grew, looking at the dendritic tree ring. So we can recreate past climates by interrogating these different surfaces on the Earth. We also have models, and models allow us to take the mathematical understanding of how a particular part of the Earth system works and put it into a mathematical representation of how that functions. The Intergovernmental Panel on Climate Change, which is a group of scientists that are oriented from all of the world's countries, have brought together a number of general circulation models, which are our largest scale models. And these are the ones that are used to make predictions about what the climate has been in the recent past, what it is now, and what it is going to be in the future. So that's the benefit of a model, is you can look at it and go into the future with these models. We also have high resolution climate models, which will take climate of a particular region and look at it from a mathematical perspective for a very small localized area. Like we can have a climate model for the prairies of Canada, or we can have a climate model for Baffin Bay, or we can have one for the Sahara region of North Africa, that kind of thing. And all of these different tools help us understand how the planet is evolving and how it is changing, but it also allows us the ability to look at the relationship between our economies. Our economies are reliant on fossil fuels, and how these fossil fuels make their way into that blue limb, and what they do when they get into that blue limb in the context of raising the temperature of the surface of the planet and affecting the climate system of the planet. Right now I can tell you that the Earth's surface has increased by somewhere between 0.5 and 0.8 degrees Celsius over the last 150 years at a global average level. So a global average level, that doesn't sound like very much, right? It's a pretty small change, 0.5 to 0.8 degrees Celsius. But remember, that's an average over the whole planet. You and I were sitting underneath the Wisconsin ice sheet 15,000 years ago, and the global temperature was 4 degrees colder than it is today. So globally, 4 degrees cooler puts you underneath the Wisconsin ice sheet. 4 degrees warmer is sort of the projection of where we're going, and most of the climate analysis that's being done on the planet today says that we do not want to exceed 2 degrees Celsius as a warming at a global level. Now, my own research is in the Arctic, and I started working in the Arctic. You can flip it over to the next one there, James. I started working in the Arctic about 30 years ago. So the gray beard and the gray hair is because I've been in the Arctic for that long, and doing research in the Arctic is difficult at times. But I went there 30 years ago because these general circulation models that predicted what the climate of the Earth was going to look like, they told us 30 years ago that we should see the first and strongest signs of a global scale signal of a warming planet in the Arctic. It's called polar amplification. And so I got very interested in sea ice. This is an animation of sea ice. If I can borrow your pointer there for a second, just to get your geography straight. That's Greenland, that's Baffin Island, this is the Canadian Arctic Archipelago, that's Alaska, this is Russia, Northern Europe is down over here, this is Svalbard, Iceland over here. This is the sea ice in the middle of the Arctic Ocean. That's looking down at the North Pole because the satellites can't view directly at the pole because of the orbital geometry of how the satellites move around the planet. And you'll see the ice grows out in the winter, and then it shrinks back towards the pole in the summer. You see large export pathways here in Fram Strait, here and there Strait. You see lots of motion of ice here in the Beaufort Sea. This is the growth and decay of ice in Hudson Bay. And that sea ice has been changing very dramatically. And that's of great interest to the world because the sea ice responds both to how the ocean temperature affects the ice as well as how the atmosphere affects the ice, because it's the interface between those two in the Arctic. So if we have a warming ocean, we're going to melt the ice. If we have a warming atmosphere, we're going to melt the ice, and there's lots of complexities to that. The motion and the consequences of this change in ice we've been studying now for 30 years. In the first 10 years of my career, I felt that there was no signal at all in the high Arctic about this changing ice. And I said, well, people would ask me what's going on with climate change in the Arctic, and I was very skeptical that anything was happening at all. The next 10 years, the variability in that icescape, that's what we call it, an icescape analogous to a landscape, it started to become highly variable the next 10 years of my career. There was lots of variability in the system. And this is stuff I could see just by being there and walking on the ice. The last 10 years of my career, it's been a very precipitous decline in the amount of multi-year sea ice we have in the northern hemisphere. So significant that I'm getting extremely concerned about it because we've gone from an Arctic basin that used to have 85% cover of multi-year sea ice. And just to put this in context, multi-year sea ice is about twice the thickness of this ceiling from where I stand. It's very, very thick, very, very hard, and is a deterrent to any kind of shipping or industrial activity in the Arctic Ocean. It is being replaced with first-year ice, which is about the thickness of me. Not this way, this way. So it's about the height of me, right? So it's about 2 meters thick. And this ice is very easy to design and engineer around because you can break it, you can make icebreakers that can go through it. And a lot of people say, well, this is a very strong signal of what's going on with change in the Arctic sea ice. And we have many dramatic examples in research about how different this reduction is in sea ice than anything else we've ever seen. So for instance, we're on a trajectory right now for a seasonally ice-free Arctic. That means this ice will deteriorate towards the pole in the spring and it will completely disappear. We'll have an open ocean for a little while at the end of summer, and the ice will start to grow again the next year. As far as we know, that has not happened for at least 1 million years. 1 million years that hasn't happened. Now the next thing is there's just a paper came out just a week ago in Nature that looked at, well, how unusual is this over the shorter time scale? Let's look over the last 1,500 years. And is this reduction that we're seeing, what is it like in that context? Like we have the medieval warming period that happened several hundred years ago. You know, is this part of a natural variability in the system? And unfortunately, we are way outside that natural variability. That was the results of this paper that was just reported a week ago, which shows that this reduction that we're seeing in sea ice is unprecedented over the last 1,450 years. And the reason that we use that date is that was the period to which the paleoclimate records were able to extend this back in time. We don't know what happened at that level of detail before that. We only know that it was about 1 million years ago that we actually had a seasonally ice-free Arctic. So my role in this thing, when I talk about climate change, and I do talk about climate change a lot, my role is to do the science to understand what is going on with that system in the high Arctic and to communicate it to people like you guys, to people who live in Winnipeg, to people who live in Manitoba, Canada, and globally. And I believe that I have to continue to do this because the evidence that we have in the Arctic is that the rate of climate change is unprecedented in the instrumental record, in the paleoclimate record, and it is evidence for an early and very dramatic global scale climate change. Thank you.
Thank you, David. Dr. Brooke Milne is an assistant professor of anthropology in the Faculty of Arts. She's an archaeologist, an emerging leader in the analysis of Canada's earliest Arctic hunter-gatherer populations and stone tool technology. Brooke's recent research in the Arctic and subarctic will digitally record and preserve archaeological sites and artifacts, particularly where these resources are threatened by changing climatic conditions and encroachment from industry with interests in hydro mining and gas exploration. Brooke?
So I'm guessing most of you are wondering, what on earth does archaeology have to do with the discussion on climate change? Well, it's actually relevant in two ways. First, archaeology and the related field of paleoanthropology are uniquely capable of studying how the human species has adapted to climate change for millions of years. With this long-term perspective, archaeology can offer important insights on how humans have dealt both successfully and also unsuccessfully with major climatic events over time. Secondly, because the archaeological record consists of all things left behind by past peoples that are preserved in or on the earth, climate change threatens the very existence of the heritage resources that comprise our collective humanity. I'm going to discuss both of these points in a little more detail for the time that I have remaining. Archaeology. Well, very simply, archaeology is interested in old things. And what I mean by old, things that are older than the 5,000-year mark that we typically associate with the advent of writing. This gives us the ability to study human history long before written records existed. For the vast majority of our existence as a species, human beings, like all other animals, have lived closely to the natural environment. People are animals. But we're animals with a difference, and that difference is culture. It is the development and continued refinement of culture that has provided our species with our greatest adaptive buffer to the environment. Culture, it enables us to deal with the conditions and contingencies we face in our lives. Some archaeologists and paleoanthropologists argue that climate change is the central catalyst that has made human beings what we are today. To quote Dr. Rick Potts, humans are creatures of climate change. For example, a major evolutionary event is now argued to be closely linked to climate change, and that is the emergence of anatomically modern human beings, so us. Recent archaeological evidence suggests that modern humans first appeared approximately 200,000 years ago along the coasts of southern Africa, where conditions favored a marine-based subsistence economy. It seems that populations were moving from neighboring grasslands and tropical areas due to massive and prolonged droughts that made these areas uninhabitable. This climatic event is now believed also to have contributed to widespread population decline among African hominin populations, creating a sort of evolutionary bottleneck. Now, this maritime adaptation required new ways of thinking and new ways of doing, which led to corollary developments in culture and also in technology. Eventually, modern human beings, our ancestors, left Africa equipped with flexible, adaptive cultural strategies that enabled them to go out and compete with the descendants of an earlier African exodus, the most famous of whom we know as the ice-adapted species Homo neanderthalensis, or otherwise the Neanderthals. Now, since then, modern human beings have used culture to colonize nearly every region on the earth. Moreover, culture has enabled humans to adapt to changes in those environments. However, not every adaptation has been successful. We've seen archaeologically the collapse of many civilizations due both to natural and anthropogenetically induced events. These include the Mayans, the Easter Islanders, the Moche, and also the Anasazi. Now, where I work in the Canadian Arctic, climate change is linked to every major cultural migration, transformation, and even cultural extinction throughout this region's 4,500-year history. But in places like the far north, climate change as we are experiencing it today is impacting the archaeological record in such a way that we may lose the chance to study the past unless we can find ways to stabilize sites. Now, the Arctic is a unique region for archaeological research for several reasons. Firstly, because of the permafrost. Oops. There we go. Because of the permafrost, we get excellent preservation of really delicate organic artifacts that are made of bone, antler, ivory, skin, sinew, and so forth. even such delicate little things as tiny bone needles that would have been used for sewing hide clothing. Now, the region is also unique because it has a long history of human occupation. So about 4,500 years in the eastern Canadian Arctic and much longer within the Alaskan Arctic regions. Overall, the population density in the Arctic has been low, meaning fewer sites have been disturbed by other populations afterwards. And lastly, because of this low population density, infrastructure growth has also been slower as well. So you don't have sites being threatened the same way that you might say in the 400 series corridors of highways in southern Ontario. Now, as such, archaeologists have the potential to examine culture change and human adaptation in one of the most challenging environments on the planet. In 2010, I received funding from the Canadian Foundation for Innovation to acquire geophysical survey and digital microscopy equipment that will be used in a pilot project focusing on a large archaeological site known as Sunnah Route, which is situated on the southeast corner of Bylot Island in Nunavut. Now, this site has been occupied for millennia, and it has contributed much to our knowledge of Nunavut's rich culture history. But the site itself is in trouble. And by that, what I mean is that it's in trouble because of melting permafrost. So the site itself is located on this little peninsula here. So because of melting permafrost, the deposits are starting to slump. And because of the position of the site being very close to the Arctic Ocean, cultural deposits are actually eroding into the water. So this is frightening, really, from the standpoint that archaeological sites are non-renewable heritage resources. When they are disturbed or destroyed, they are gone forever. You can never recreate the information that has been lost. Now, two of my colleagues, Dr. Robert Park from the University of Waterloo and Dr. Douglas Stenton, who is the Director of Culture and Heritage for the Department of Culture, Language, Elders and Youth for the Government of Nunavut. We are in the planning stages in order to work with geophysicists and engineers to create a stabilization strategy for the Sunnah Route site. Now, the goal of this pilot project is to preserve the site in situ. So what I mean by that, to preserve it in place. And this allows future generations in order to access the site and also for future research to take place. Now, current estimates suggest that the number of sites that we know of in the Arctic today actually comprises only 5 to 10% of what actually is out there. So this further underscores the need to find ways to preserve the sites that are out there before they are lost. Now, climate change threatens the stability of all kinds of archaeological sites worldwide. And archaeologists are endeavoring to carry out similar kinds of pilot projects in order to protect the archaeological record. Now, archaeology is a field of study. Well, it's exciting. I think it's exciting. As a teaching tool, it is especially effective since youth can hold in their hands a piece of the past that connects them to the land, to their heritage, to their ancestors. A memory I have from 1998 when we were working on a site called Tungatsivik just outside of Iqaluit. I was working with a young Inuk boy who was excavating in the soil, and he came across a tiny stone flake that was part of a Dorset stone tool. And he looked at me and he said, "I've been waiting my whole life to find this." Now, archaeology, it does have much to contribute to a discussion on climate change since it has shaped our species for millions of years. And looking to the past, we can attain valuable perspectives on how our modern societies can adapt to the new challenges we face now. Archaeology can also engage current and future generations in a dialogue so as to awaken their consciousness about what is really at stake. As a species, we are short-lived compared to our other hominin ancestors. We are still evolving, and we are still adapting to climate change. However, what remains unknown is whether or not we can successfully adapt to our present culture to meet the challenges we are now facing.
Thank you, Brooke. Dr. John Hanrahan is a professor in the Department of Environment and Geography at the Clayton H. Riddell Faculty of Environment, Earth and Resources. He's a Natural Sciences and Engineering Research Council of Canada scholar and a specialist in atmospheric science with expertise in surface-atmosphere interactions, storms, extreme and hazardous weather. He uses a combination of field work, computer modeling, and remote sensing in his work. He has been part of over 10 major national and international projects during his career, ranging from severe prairie thunderstorms to Arctic storms. John?
Thanks, David. Well, I'm going to talk a little bit about prairie thunderstorms and how we think things might look for the future here and also for the States as well, particularly. So just to go over some of the 4 ingredients are basically needed for severe type thunderstorms. One's moisture. We've all felt that in the summertime. Hot, humid days, you get thunderstorms form some days you don't. So we all know we have to have that sort of low level moisture to supply that feed of fuel for storms. So that's what moisture is basically providing the fuel for thunderstorms. Next is instability, and I'll sort of show what that sort of is in just a second. But basically, as you, for those Kelowna East students here, by the way, I'm from Kelowna East, so it's my old stomping grounds. So the physics students here, physics actually does matter. It applies to the atmosphere, which is what I study. And the first and second laws of thermodynamics are basically, they sort of dictate how parcels of air, what they do when you lift them up in the atmosphere. So when you start them from the surface, what is their temperature, how does their temperature change as you lift them in the atmosphere? So instability is basically comparing this parcel of air as you're lifting it in the atmosphere to the outside environment. And I'll give an example of what that looks like in just a second. The third ingredient is some sort of lift mechanism. So you need some sort of a front, cold front, warm front, or some sort of mechanism to lift air up from the surface up to higher levels. So that's what's usually called a trigger. So you need some sort of mechanism to lift parcels up in the atmosphere. So those 3 ingredients you need are for thunderstorms in general, any kind of thunderstorm. These 3 ingredients you need. The 4th one basically dictates how severe that storm is, what's called convective mode. So what kind of storm you get. And that's what wind shear is. So wind shear is looking at how does wind speed and direction change as you get higher in the atmosphere. Right? So the stronger the winds change in speed as you get higher in the atmosphere, the more conducive that is to severe storms. And if you get a strong directional change in the lower part of the atmosphere, that's also conducive to tornadic type storms. So these 4 things are the basic primary ingredients for severe storms. So what the question now is, and what people are asking is, how are these 4 things going to change in the future with climate change? Will they change? How will these 4 things change in the future? And that's what it sort of boils down to. And like Dave was talking about before, global climate models are large-scale models. They have larger sort of grid scale. So trying to understand what a thunderstorm is a very localized thing. Thunderstorms can occupy 5-kilometer widths to maybe 15, 20 kilometers in sort of horizontal extent. So climate models right now are not, their resolution is not quite good enough to get down to the scale of a thunderstorm. But there's other things that we can look at. These 4 major ingredients, we can sort of infer from some of the climate model information, particularly regional climate models, which Dave was talking about, sort of the smaller scale climate models in general. So we can get a little bit of a handle on some of these things and how they might change in the future using these types of models. Okay, that didn't turn out very well. So what we have here is if you took a weather balloon and launched it up in the atmosphere, this is temperature scale here on the bottom, so you're increasing in temperature along here, and this is height. So if you launch a weather balloon and you measure the atmospheric temperature, this is what the profile might look like. You know, it's decreasing and then increasing here a little bit. Usually the top of the boundary layer, you get this sort of increasing part of the atmosphere, which is called the cap. And then it decreases thereafter. And this might be the trace of what the moisture content of the atmosphere looks like. So it's what the dew point temperature is. Right? So this is the moisture curve, and this is sort of the air temperature curve. So let's look at to see what the, if you lifted a parcel off the surface, what it would do. So this red curve represents what the parcel of air would do if you lifted it from the surface. Okay, so it'll follow the ambient air temperature. So this is what that trigger needs. So the trigger has to lift the parcel from the surface up to this point here. This, you can sort of see where this red line becomes on the right side of this curve is where that parcel air temperature becomes warmer than the outside environment. So it's going to be buoyant, right? So it's going to be like a hot air balloon. You heat a hot air balloon. If you heat it enough, it's going to be warmer than the outside environment, and it's going to accelerate upwards, right? That's how hot air balloons work. And basically that's how severe storms or thunderstorms work, is those parcels of air are warmer than the outside environment, and they rise very rapidly. And that vertical acceleration upwards is a function of how different the temperature is from the air parcel to the outside environment. And that's what instability is. So an unstable atmosphere is when the parcel is much warmer than the outside environment and it rises basically on its own positive buoyancy. So it's basically natural free convection. So the role of the trigger is to get those parcels up to this level here that's called the level of free convection. So the level of free convection is where that parcel becomes positively buoyant or warm in the outside environment. So that's what the role of the trigger is to get that parcel to where it needs to be to form a thunderstorm. Now if we change the moisture content of the lower part of the atmosphere, what will that do? Well, first of all, it's more humid, so we'll feel that. And the other thing it'll do is it'll change our level of free convection. You notice here that the parcel temperature now is lower to the ground here, and the parcel of air is actually warmer than the outside environment right from this lower level as opposed to up in here. So you need less of a trigger to get that parcel going, first of all. And there's much more energy. The difference between the parcel temperature and the outside temperature here is much greater. So that buoyant energy is much more stronger in the magnitude. So you get more severe storms. So there's actually a fairly recent paper that's come out and looking at how instability might change in a future climate. So one of the things we're going to see in the prairies and all across the central part of continents and around the world is an increase in surface temperatures. And that's going to essentially increase our instability in the atmosphere. When you increase temperatures, you're also going to increase the moisture content, right? So the warmer the atmosphere is, the more moisture it can actually hold, per se. So the future is warmer temperatures, potentially more moisture in the atmosphere, producing more instability and producing potentially more energy for storms to form, if they do tend to form. Right? So that's one of the things that that's been recently found to play a role. So now on to wind shear. I'll just briefly go through this. This is what's called an air mass thunderstorm. It sort of shows you the evolution of a thunderstorm. From the initial stages, you get precipitation forming once the storm gets in its mature phase. It creates precipitation, it falls out to the ground, and it essentially kills the initial updraft. So when the storm is first forming, it's all updraft, right? So it's very positively buoyant. All the air is moving upwards in the storm. You're getting precipitation being formed here. It starts to fall out, and it kills the updraft or the energy, the buoyant energy that's there to supply that storm in the first place. So this is what happens when you have no wind shear. So if you have winds that are not changing in speed as a function of altitude or direction, then the thunderstorm will grow and it'll essentially kill itself off in about an hour and a half. It's gone. If you get wind shear happening, what will happen is this storm will tilt over. Right? So if you get stronger winds as you get higher in the atmosphere, it'll tilt that storm over and it'll separate the downdraft or the precipitation area from the updraft area. Right? So that storm will tend to persist for a longer period of time. So let's go to this one, and that's what this is sort of showing here. You have a strong updraft area and a strong downdraft area. This kind of a supercell type storm is created in an environment where you have strong vertical wind shears. So strong winds aloft and weaker winds below. And so that'll tilt the storm over essentially. What separates usually tornadic storms or severe tornadic storms from just sort of regular thunderstorms is a strong directional change in wind from the surface up to about 2 kilometers. So if you get a strong wind, say coming from the southeast or the east in the low levels, and then it curves around and it's actually blowing from the southwest at say a kilometer and a half above the surface, you get a strong directional change in that wind field as well. And that's what's prone to strong tornadic type storms. So there's the 4 ingredients. So the question is, how are those 4 things going to change in a future climate? So one thing I've touched upon already is the moisture. So moisture we're expected to see will most likely increase from local sources and from movement of moisture from other parts of North America. So we'll see probably an increase in moisture, increase in air temperature, which will also add to the instability factor. So those 2 things. The other is the trigger. What's going to happen with the triggers? Well, it's a good question. We don't really know what's going to happen with triggers. Triggers are, like I said, fronts, intense weather systems. So for example, if you get a strong, intense weather system, the fronts and frontal boundaries tend to be stronger. So you tend to get stronger lifting mechanisms. And the last is the wind shear. How are the winds going to change in a future climate? And there's been some studies to suggest already looking at what are called low-level jets. So low-level jets are where you have very strong wind flows that are existing between, say, 1 kilometer and 1.5 kilometers above the surface of the Earth. And those low-level jets are supposed to be increasing with the future climate. And those are conducive to tornadic type events and stronger type storms in terms of how basically tilting of these storms in general. So there are things out there that we can sort of pull from the climate models and to suggest how things might change. So, thanks very much.
Thank you, John. Dr. Paul Bullock is a professor in the Department of Soil Science at the Faculty of Agricultural and Food Sciences. He teaches in the areas of agrometeorology, micrometeorology, and soil and water management. His research has included quantifying impacts of weather on crop performance, as well as the development and validation of models for the prediction of these impacts. He has experience in the grain industry and operational crop yield forecasting as analyst and director of the Weather and Crop Surveillance Department of the Canadian Wheat Board. Paul?
Thank you. Well, it's a pleasure to be here and to represent the agricultural side of this particular discussion. I'm very proud of being part of that particular profession in the business of feeding people. And what I want to talk about tonight is the issue of feeding the 9.5 billion, okay? 2,000 years ago, feeding 5,000 was a miracle, okay? So just put it in perspective. Now, we've had a surge of publicity around our population reaching the 7 billion mark. And really, on one hand, I have to admire our collective ingenuity. It's impressive that we can actually produce and distribute enough resources to support this many people. And it certainly hasn't been perfect by any means, but there's many who thought it couldn't be done. And fortunately for all of us here, Malthus got it wrong, right? 200 years ago, he looked around and said, the world is finite, and this is going to impose a harsh resource-limited cap on our population, and it didn't materialize. And even the modern Malthusians that were predicting mass starvations at the end of the 20th century were incorrect. So it seems that even though our Earth's resources are finite, our intellectual and adaptive capabilities have so far overcome those limits. Now, on the other hand, I've had the experience for the last more than 20 years to witness the remarkable results of the Green Revolution. And year after year, we've seen global crop production levels rise to keep pace with this demand from population growth. But now, those yields are showing signs of stagnation. And I'm starting to wonder, is our challenge for feeding the population in the 21st century finally going to outstrip our ingenuity? And I want to make sure that there's no mistake about this. The task that we face is like none we've ever done before. We expect to add an additional 2.5 billion people to the table by the middle of the century. We are supposed to feed them good quality food from a land base that's already largely utilized, using environmentally sustainable production practices and making whatever adaptations we need to climate change with a shrinking water supply. This is no easy task, and we better get it right. Now, we happen to inhabit right here an area of the Earth where crops could potentially benefit from climate change. I found that fascinating. It's an area that I wanted to look into. Western Canada faces crop production limitations from a semi-arid mid-continental location. We have highly variable rainfall, a relatively short growing season, and a limited supply of heat. And at first glance, prospects for a warmer and a wetter planet might appear to be positive. However, as with most things, it's not quite as simple as it might first appear. Yes, warmer temperatures should increase the length of our frost-free period, and that should add some heat that will allow us to support higher yielding crop species, so that's positive. But those same higher temperatures will also facilitate increased pressure from insects and disease pests. They'll be able to overwinter, that are going to be able to produce more cycles per growing season. Yes, higher levels of atmospheric carbon dioxide is useful for water use efficiency and improves it, and seems to particularly enhance the amount of biomass we produce from our C3 crops like wheat and canola and barley and rice. But in the majority of research trials, weed species tend to benefit more than our crops when we give them higher CO2. Now, yes, we can control them with herbicides, but those same studies, some of the same studies are also showing that herbicide efficacy goes down with increased CO2. So do we really want to use that much more pesticide to try to control this? It's a good question. Another question is the exact nature of the change that we face. Weather patterns have significant spatial variability, and they've exhibited that in the recent past. It has not become warmer and wetter everywhere. And a piece of ground that you happen to be farming, what matters to you is what is it doing right there. Most of the recent warming in Canada has occurred in the fall and in the winter. It has been a result of warmer overnight low temperatures rather than increasing daytime highs. Recent rainfall patterns are shifting to becoming longer dry periods spaced between short bursts of heavy precipitation events. And this creates a very ironic situation with an increasing risk for crop damage from both drought and from heavy rainfall. Over the course of reviewing this, I've compiled two lists. One highlights the potential benefits that we could see in Western Canada from climate change, and the other one highlights the potential limitations. And guess what? The length of those lists are pretty much equal. Furthermore, there is very little research that looks into interactions. Okay? We know higher CO2 tends to favor C3 plants, but warmer temperatures tends to favor C4 plants like corn. We know that at higher CO2 levels we tend to get bigger, larger root to shoot biomass ratios, but warmer temperatures we get the opposite. So where does that leave us? And we don't have answers to these in a multitude of similar questions, so it's very hard to predict what's going to happen. Now, to illustrate, what I wanted to do is to show a recent estimate of a climate change impact on future global GDP. I'm not just sure exactly how I do that. And down again. Ah, there we go. All right. Now, this picture, this is a fairly comprehensive study, paints overall a slightly negative picture of the future for global agricultural productivity. Globally, it's down about 3% in 2080 compared to 2003. And if you look at that map, unfortunately, you can see that most of the decline is in areas of the world that can least afford a decrease. Now, if you notice up where we are in Canada, we're actually on the positive side of the equation, as are many of the production regions along the northernmost tier of the Northern Hemisphere. However, one of the assumptions in this picture is that higher atmospheric carbon dioxide will increase C3 crop biomass production by 15%. Okay, that's one of the assumptions in this. The author recognized some of the uncertainty that exists around that particular estimate. You know, just as an aside, it turns out, by the way, that plants are much like humans. They're lazy. Okay? You put them in the ground at high CO2 and let them grow, and guess what? The leaves that they produce have fewer stomata. You know, they don't put as much energy into that CO2 exchange. And, you know, I guess that probably makes sense from an adaptive perspective. Anyway, this author asked, what if we're wrong? What if higher atmospheric CO2 doesn't give us anything? What if there's no net positive effect? How would that affect my analysis? So we did it again. The previous map was slightly negative. This map is catastrophic. Okay? In Western Canada, we shift from the positive side of the equation to the negative side. On a global scale, this is talking about an 18% decline in agricultural productivity, and that is an absolute disaster. Now, I'm not saying that this is correct. We don't know for sure. Nobody does. My point is that you change one single assumption, and in this particular analysis, we get this enormous ripple effect that completely changes the outlook. And unfortunately, we have to make a lot of assumptions when we try to answer the question of whether we can continue to feed our population. Can we feed the 9.5 billion in the face of climate change by the middle of this century? So I certainly don't have answers. I know that up to now, we've more or less managed to stave off that Malthusian cap on population growth, basically with ingenuity and intellect. The question I'm asking is, will we manage to continue innovating sufficiently to ride out the crest of the population wave washing over this planet this century? And I don't know, but I can tell you I certainly hope so. Thank you.
Well, thank you very much, Paul. So now we're going to, I'm just going to ask the panel one question, and then I'm going to look to you for questions. I would remind you of what I said earlier. The room is full. Many people will have questions, so please keep your questions, state your questions briefly so that the panel can get involved. And I have a couple of colleagues who have microphones. They're these handsome young men in the front here who will come to you with the microphones. So let me just ask a question. I'd ask each of the panelists briefly to respond to it. Climate change is really underlying a lot of what each of you has said, but we know that this is a somewhat and sometimes controversial position. There are those who find it difficult to believe that that climate change is an established reality, and that possibly what we're seeing are time-wise local effects rather than something that's a longer-term trend. So I wonder if you could, Dave did speak to this very explicitly, but I'll just ask each of you if you might speak about your confidence with which, the confidence level with which you hold to your position that climate change is actually occurring and affecting the work that they're doing. So Dave, you already started. I'll let you start again.
Me to take it up? Okay. Well, from the Arctic perspective, we pay a lot of attention to this because the whole world is paying attention to what's going on in the Arctic as far as variability and change. It's really important to think about the fact that climate change is part of our climate system. It's always changing, and it always will change. The issue here is the change that affects the human society and civilization that we have, this 7 billion we have going to the 9 billion. So you need to think about the kind of scales of humanity. And so I always tell people climate change has nothing to do with the planet. It only has to do with people. The climate will continue to change long after we're gone. From the perspective of sea ice and the changes that are going on with sea ice, we are very confident that the changes that are going on there are unprecedented over the last 1,500 years. The magnitude of that change and the rate of that change is something we're very confident in based on scientific analysis that's been done over the last 15 years primarily, with most of that research being done in the last 5 years. And I think that the idea that we were looking to the Arctic to see the first and strongest signs of climate change make me very concerned about what's happening at a global scale as well. So I like to look at the Arctic as almost like a canary in the coal mine kind of situation, and it gives me concern about what is happening at the rest of the planetary scale. Now, there is a lot of uncertainty in that, and there is no absolute truth to it. It becomes an issue of using science in sort of an analogy of a crystal ball. That crystal ball gets clearer and clearer as we get the science better and better. But at some point, you have to start making decisions about risk management. And I think Paul alluded to that very clearly about the risks that are associated with this. So did John, and so did
Brooke.
So did Brooke. Sorry, Brooke. I wanted to say B. And this risk management is an issue that we have to deal with as a society, because we have to deal with the uncertainty not only of the science, but also the uncertainty of the future, because we're on a future trajectory that could make things much worse if we don't do things now.
Thank you. Brooke?
Well, I think probably how I will start answering this question is anecdotally. And based on my own experience, I've been lucky enough to participate in archaeological field projects since 1996. And over the course of that time, certainly we were looking at the archaeological record, but living on the land provided some interesting perspectives about what the climate is like. And the things that stand out for me, in 2002, 2003, we were working on a project in Igloolik, which is by many respects considered one of the heartland areas of Inuit culture in the north. And when we were there, we heard thunderstorms. We didn't think it was possible to hear thunderstorms in the Arctic. And at the time, little kids in the community, even adults too, were pretty uncomfortable by what that thunderstorm was like because they'd never heard it before. In 1998, we had one of the driest seasons that we can ever imagine, so much so that we even had trouble finding water, just potable water from places that we knew that we could always find it. 2007 was the wettest field season that we had ever had. Of 28 days, we lost 12 of them to weather. So I know that that's not hard and fast science, but anecdotally, from my own experience, there's strange stuff that has been going on when we've been up living on the land conducting excavations. From a more pragmatic standpoint, the archaeological record certainly is indicating that there are problems. Permafrost, which is perennially frozen ground that's always been frozen, is melting. And the active layer every year that we have that just goes through the natural seasonal freeze-thaw cycle, the active layer is actually expanding. What that's doing now is for archaeological deposits that have always been frozen are now becoming exposed to this natural freeze-thaw cycle, and they're basically getting churned up and destroyed. The fact that we have sites slumping into the Arctic Ocean when it hadn't happened for 5,000 years possibly beforehand is a bit disconcerting. So I think that there are things that certainly are happening, absolutely. And the kind of research that David is doing, among other climate scientists, certainly seems to support that fact, absolutely.
Thank you. John?
Well, briefly, I guess just to continue on with the extreme side, there's actually just a fairly recent report that came out, and there's given an address at the American Geophysical Union, and I'll maybe just read a couple of passages here. Frequency of extreme events has risen steadily over the past 20 years. The number of meteorological and hydrological events has tripled in that time. Large-scale climate change is also likely to affect small-scale phenomena like severe thunderstorms and tornadoes, but the nature and degree that influence are very uncertain, particularly for tornadoes. We've definitely seen more extremes and more variability in the climate system over the past 30, 40 years, and there's no questioning that. I guess some of the climate change people, maybe not sort of convinced of climate change effects. Is it human-induced climate change or not? I guess that's what the main question is. And over the past number of years, the IPCC and all the evidence is suggesting that there's no question that it is human-induced change. We have not seen the increase or the sharp increase in temperatures that we've seen over the past 50 years. It can't be explained by natural variability. We've never seen an increase in the temperature that we've seen on a global average, or even in some regions, as sharp as increases as we've been witnessing. And it can't be explained totally by natural variability.
Okay, thank you. Paul?
I think there's already been some comments made here about variability. This is one of the other things. I think that in the Arctic, you do, like the canary in the coal mine that you mentioned, Dave, I think is very much the case. You can really see it clearly there. We have to remember that climate is composed of weather, and weather is highly variable. And you know, you talked about the change from the dry to the wet, and how'd you like your soil moisture in 2011 in Manitoba? I mean, we went from floods, farmers collecting money for not being able to plant because of excess moisture, and what they did plant, they got drought relief on, you know, in the same year. So that kind of variability does two things. One, that makes it very difficult sometimes to find trends buried in all that variance, but the variance itself creates huge problems. And I mean, I think that we've had some examples here. Maybe they're anecdotal, like you say, but that something's going on, and it's put quite a challenge to us.
I could just add something to that. One of the things I didn't mention in my opening remarks was that the general circulation models predicted this amplification in the Arctic, but they also predicted this increase in variability in temperature and precipitation, and we're seeing all of those things happening now based on model projections from 30 years ago. So,
great, thank you. If you have a question, please raise your hand, and one of my colleagues will find someone. All right, we'll go over here first.
Hello, thank you. My name is Ian Robson. I drove in 3 hours this morning over icy roads, and I'm a struggling peasant farmer, and quite concerned about the future food security. It's been mentioned about cultural change as a result of shifts in climate or shifts in certain situations. I had the opportunity to attend the Farmers Union Convention in Ontario last month. Ellen Gabriel, Iroquois leader, spoke to us about food sovereignty. And she explained that about 75% of the seeds, the vegetable seeds that the Iroquois Nation used to raise their crops, and they were an agricultural community, 75% of those seeds, the varieties, are extinct. So the rest of the population is surviving on 25% of the varieties that were in existence. So our seed supply is at risk. Our ability to move onward, I mean, you might think of Mars as another opportunity. I don't. Ellen Gabriel put it this way: does the Earth belong to you, or do you belong to the Earth? And the natives would tell you, we all belong to the Earth. So we have to get our act together and start thinking a little better. Gwyn Dyer has a book about climate change where he's suggesting SO2 might be the result of too much CO2 collecting in the atmosphere. The atmosphere might shift over to becoming a sulfur-based atmosphere.
Thank you. Others? Chris, right here.
Thank you. I have a question for Dr. Barber, actually. Now, looking at a lot of the things that have happened in the Arctic, it's very clear that things are changing very quickly. And from what I understand, the Arctic sea ice or polar sea ice acts to reflect a lot of sunlight and heat. And as that melts, it actually increases the warming. So I guess there's two parts of that. A, is there some point where these increased warming will actually stop, or will this positive feedback continue on until we can't survive on the planet? And B, are any of our efforts that we're actually making now actually able to stop what's already started?
Okay, I'm going to stand up for this one. It's a long answer and I got to stretch my legs. You're right, absolutely. I mean, you have a white surface that reflects lots of solar radiation, then you have a dark surface. And we overwintered on the Amundsen during the International Polar Year last year, and we were the first group on the planet to have a fully outfitted research icebreaker that stayed mobile right through the whole winter in open water in the Arctic. Not because we do anything unique, but we had a good opportunity with IPY, we had the funding to do it, we had the infrastructure, but also the ice allowed us to do it. So historically you could never do this, you couldn't even think of doing something like that. When I went to the Coast Guard to suggest the project, they said, there's no way, you're going to crush our ship like a tin can. And as it turned out, the temperature where we were in the southern Beaufort Sea was systematically warmer all winter than it was here in Winnipeg, because there was so much open water, you were just getting this heat flux from the ocean. So what happens is you remove this ice cover, The solar radiation is absorbed by the ocean. That puts heat into the surface mix layer of the ocean. It then is advected underneath the sea ice, which melts more sea ice. And so this feedback has been going on, and it's much more complex than what I just described, but that gives you the general idea for it. But you have to remember that so long as the Earth tilts towards the sun for our summer and away from the sun for our winter, we will always have sea ice in the northern hemisphere. The thing is that it will be first-year sea ice, and so this ice will be much thinner, it'll be much more variable, it'll be something that, you know, people can engineer to ship ships through and stuff like that, but we will shut off that albedo feedback effect because it will be dark. And so you won't be getting energy into that. Even if you had an open ocean right through the winter, you would be getting very little energy into that open ocean. And then of course, as soon as you have no sunlight, there's no energy source, so you start to form sea ice again. So when we talk about a seasonally ice-free Arctic, it's only going to be for a short period of time. It may exist for a week or 2 weeks or 3 weeks or 4 weeks. But if I'm standing here talking to an audience like this and we have no sea ice in the northern hemisphere in January, we have a very, very serious problem on our planet globally. And so the Arctic isn't going to do that. It's not going to be this runaway kind of effect that is going to cause the temperature to change dramatically. What it will do is it will add to the global temperature rise that is going on right now. And in fact, one of the things that gives me concern is that the IPCC assessments that are done for a seasonally ice-free Arctic, all of them show that we should run out of sea ice in the northern hemisphere in the summer somewhere around 2100. Now right now, the model or the observations for that show that we're going to run out somewhere between 2013 and 2030. So we're way ahead of the model projections of when we'll have a seasonally ice-free Arctic. So that means that the models are feeding back into the global climate system the fact we have a reflective ice cover in the Arctic in the summer, which we don't. We don't have it right now. Right now we're starting to absorb a lot of energy into the surface mix layer of the ocean to such an extent that the Chinese icebreaker in 2010 went up Bering Strait, figured they could get to about 75, maybe 78 degrees north, where they would run into this thick multi-year pack, would have to turn around and go back out again. They continued all the way to the pole because the ice was so heavily deteriorated that there was no barrier to their ship, which is simply an ice-reinforced ship. So you could have went across the pole with an ice-reinforced vessel last year. And so that feedback system has local implications at that scale, but we don't have to be worried about it, you know, being a catastrophic kind of relationship. It is something that's going to help push the temperature up globally in the short term, but in the long term it will balance so long as that planet always tilts away from the sun and we get polar night in the Arctic.
Great. Thank you. Down here, Chris? Oh, I'm sorry. All right, sure.
My name is Vec Coral. I was a prof on campus, exercise science, and Dave Barber used to ask me very challenging questions so I could see where he is today. I want to apply the KISS principle, keep it simple. Dave, you mentioned that the melting of the ice is due to the water temperature, atmosphere temperature, produced CO2 causes that. On the other here that if we remove the forests, but then the wheat absorbs it, is there a balance? Also, the sun is getting hotter. It's getting hotter every day, and eventually we will all fry. Are you following the sun temperature in relation to your theories on global warming? And the other thing is, humans produce a lot of CO2. We breathe in, there's 0.03% of CO2 in the air we breathe in, we breathe it out, it's 2 to 3%. So if we stop breathing, we can solve the problem.
Great. Thank you.
I'll hang on.
Klaus Rogerman. The question for Dr. Bullock. You ascribed the success, the extraordinary success of feeding 7 billion people to human ingenuity. And I wonder whether it was human ingenuity combined with something else, and that is that during this time we banked partly on the future. We took away non-renewable resources at an incredible pace, like energy, rainforests, water. We created more poor soil, I mean soil deterioration, soil erosion, and that obviously can't go on forever. And you indicated you see already a tendency for decline. And if that's all true, then the future indeed doesn't bode well, and the planet will take things in his hands, and it will lead to massive starvation, and to reduce the number of people on the planet. And would it therefore not be maybe a more ingenious way to think of trying to reduce the number of people on the planet in a humane way rather than facing massive starvation?
Well, I mean, what you're saying is absolutely correct. I mean, when I said ingenuity, I didn't necessarily mean that was all going to be a positive thing and from a renewable resource point of view. I mean, what is it, something like 2/3 of our planet, or is it even higher than that, that has a nitrogen requirement that's filled by the Haber-Bosch process, okay? And that takes an enormous amount of fossil fuel, and the fertilizer that's manufactured is a big chunk of that green revolution that I alluded to. You're absolutely right. I mean, that's not sustainable, but there's other ways that we can apply our ingenuity. You know, we have wonderful things out there called legumes that can fix nitrogen right from the atmosphere. And there's different ways that we can innovate and do things that may reduce our reliance on some of those things that are not sustainable. And the world's demanding that, and I think we have to listen.
Great, thank you. There's a question up in the back corner.
I'm Ganpat Lodha. I'm a retired geophysicist. I think global warming is an acceptable fact based on records of observational systems. But my question is, how much percentage of it is Earth's natural cycle of warming and cooling into ice ages versus how much of global warming observed in last 10, 15 years or few decades can be attributed to fossil fuel phenomena?
Who's taking that one?
Not me.
Well, I'll give a stab at it, and then somebody can jump in. I mean, this is a perfectly valid question, and it's something that we all have to ask ourselves. I mean, is there good evidence that this is anthropogenically generated? Are people generating this change that's going on? We have a few different ways that we can look at that scientifically. So one of the most common ways is we use the models to do that. So the models, first thing you got to realize about some of these general circulation models is people say that, well, it's a model. I mean, it's, you know, everybody generates models. You can put one together on your PC and away you go. Well, a general circulation model is not like that. They're extremely complex models, and they have to meet certain requirements to be included in this suite of models that are being used to make these predictions. So they have to be able to assess past climates properly. They have to get certain processes correct. There's different tests and balances. So from the models, you can look at, okay, if we didn't have the amount of greenhouse gases going into the atmosphere that we've had over the past 200 years, what would the result be? What would it look like? So you can actually use the model to assess that. So that's one way you can do it. The other way you can do it is look at past climates and say, well, what does the climate variability and the climate state look like when we've had less CO2 in the atmosphere, less carbon in the atmosphere? And some of the paleoclimate reconstructions are very telling about what this relationship is, and it informs us about how the future climate should work. So for instance, one of the examples is the great ice sheets of the planet all formed when we dropped the CO2 level in the atmosphere below 450 parts per million. Those are when the great ice sheets of the planet formed. So the Greenland ice sheet, all the Antarctic ice sheets, those kind of things. Well, we're at about 392 right now, and we should be up to about 450 sometime by mid-century. So if you look at the variability of the different kind of analogs that we have for those in the past, we see this relationship. Now we know, just by straight measurement, that the change in CO2 concentration in the atmosphere has been generated by our reliance on fossil fuels. And it's not magic. You have all these, you're a geophysicist, we have all these fossil fuels in the ground, we liberate them into the atmosphere, and that is happening extremely quickly, and it's something we just measure, right? This is a measured variable. It's like measuring temperature and standardizing that temperature for different kinds of variables. So I think there's very clear evidence that the anthropogenic effect on CO2 in the atmosphere is very clear. It is something that has happened as a byproduct of the Industrial Revolution. And it's very clear that the climate is really sensitive to these kind of things because of the sorts of feedbacks that I've talked about and the kind of feedbacks that John was talking about with extreme weather. I think we're very sensitive to these kind of things. So my take on it is that this is something that human civilization is adding to the natural variability that exists in the climate system.
Okay.
Want to add something?
No, I don't think anyone wants to add. Chris?
Hi. I guess I've been listening to kind of discussions on climate for some time, about 40 years or so, and following environmental issues for probably 50 years or more. And I've noted that in the last decade there's been some changes in the way that we talk about the impacts of climate. For example, one thunderstorm in this past April spawned 200 tornadoes and killed about 450 people in the US. Last year, the Indus River flooded in Pakistan and killed about 10,000 people. The drought and, of course, the war in Somalia killed 29,000 children this year, and today half the population is said to be at risk. So professors like Dr. Friedman, Dr. Suzuki, Dr. Hansen of the NASA Training Institute say that we are in the process of, or on the path of killing our grandchildren. And I guess one of the things that just came out today on the Environmental News Network was that a Professor Smeltov in Russia, Igor Smeltov in Russia, made an announcement that they'd come across a great number of methane leaks bubbling up to surface, and I guess they've discovered these some years ago, and that they were originally about 10 meters in diameter or so. And now they've found one that is 1,000 meters in diameter, which he said is absolutely amazing. And he estimated that this year that the methane releases would release an estimated 8 million tons of methane, which is supposed to be a greenhouse gas about 20 times worse than carbon dioxide. So the greatest fear is that the loss of summer sea ice will lead to an uncontrollable release of methane, irrevocably changing the Earth's climate. And it seems that in this kind of context, the petroleum or fossil fuel companies are doing nothing because they want to maximize profits, and the politicians are largely doing nothing. And I guess my question is, who can I talk to join hands and try to get some action going? I'd like to simply join some kind of group that's really interested in action.
Does anyone want to speak to that? Yeah. Pardon?
Give me some leads. Who can I talk to? Who wants to be part of it?
Well, I think does anyone want to speak to this? I think we'll have to get back to you on that. I don't think that's not really what we're here discussing. But we can certainly try and help you offline. So, question at the back?
I was wondering just how much impact human civilization has on the amount of carbon in the atmosphere. Because it seems like a volcano going off would have a whole lot more impact than human civilization could.
You guys want? I feel like I'm talking too much. So.
Well, I'm not sure that I really know for sure. I mean, you're correct. You know, in the time that I was doing operational monitoring of crops, if I had to say that there was one thing that had an impact, one event, it was a volcano. It was the eruption of Mount Pinatubo in 1991, and we had snow on 3/4 of the prairie and heavy frost by about the third week in 1992 because of the high sulfur dioxide. So you can get very, very powerful impacts from, like you say, one volcano. I'm not exactly sure how to put your question about human civilization into context. Are you talking about our fossil fuel use or the carbon dioxide we breathe that Vic was talking about, or what do you mean?
Yeah, maybe I understand what you're trying to get at. I'll jump in with this as well. I mean, the thing with volcanoes is they're a point in time, right? They're an episodic event, and they put a lot of reflecting materials into the atmosphere as well as greenhouse gases into the atmosphere as well. So the cooling that happened with Pinatubo is you have a lot more reflection of solar light from all the aerosols that are associated with the volcano, and you see that effect that is short-lived. It lasts for, even in the Arctic, we saw the effect of Pinatubo in 1992, and it kept the ice in for the whole summer. But it's an episodic event. It disappears the next year because all of these aerosols all drift out of the atmosphere they get deposited onto the surface. The amount of greenhouse gases that the human civilization and the burning of fossil fuels is far larger than what you'd get from a single eruption of a volcano. So it's a different scale totally. And the greenhouse gases are also associated with aerosols, which are reflective in nature. And right now the climate community is suggesting to the world that they don't remove these particulates from gasoline, and we don't try to clean up some of the atmospheric pollution in some of the big cities, because the models are suggesting to us that these cooling effects are actually slowing down the rate of the warming. So we don't want to remove them from the atmosphere with the fear that it may cause the warming to increase even more. So you think about how many people are on the planet and how many fossil fuels we consume. It's an enormous amount.
Okay.
Just even thinking from, in terms of humanity and civilization, certainly there have been cataclysmic events that have happened, volcanoes being one of them, that have created enormously difficult situations for hominins, human beings, in order to adapt. The difference being that back then population densities were so low that people could move. So if things just completely fell apart in one area, they could actually start to migrate in order to find more amiable conditions to continue to survive. Here now, with the way that the society is structured, population densities being as incredibly large as they are, we can't move. So if something like that happened, which it has in recent memory, certainly in the historical past, it's had enormously dire effects on people's ability in order to survive.
Chris?
Hi there, my name is Caitlin McIntyre. I'm a graduate student in the Department of English. And I have a question actually about geoengineering. To me, it seems a progress stop, that it's yet another manipulation of the organism versus a sincere commitment to changing behavior. Ergo, my question is, what is your take on the efficacy and also the ethics of geoengineering?
I'm totally against it. I think it's a bad idea. For many reasons. I'm just against it.
I think
Or you're just playing with fire again. Yeah. You're not solving the problem. That's the crux of the problem, I think, right? You just you're putting a Band-Aid solution on something that's going to be, and you don't know what the effect might be down the road from those things you end up changing. Mm-hmm. So the feedbacks are the worrisome parts, where you don't understand what the feedback might be after you've done that change.
I think, too, coming back to one of the, I think it was the first comment that the gentleman over there had made relative to the proportion of indigenous species versus species that are now, I guess, taken over. That if you start messing with the biodiversity like that, it's not like you can go back necessarily, or you can't do it easily. And within different areas around the world, different cultures, I mean, we're starting to see now that governments, and please forgive me, relative to the Green Revolution, it hasn't been blanket successful in every single place around the world. Now you start seeing government initiatives where they're going back to traditional populations, trying in order to recuperate what the traditional knowledge was for how you create sustainable food sources that are adapted to the environment in which they were developed. Highland Peru, Bolivia, creating the raised fields for crops, they're called waru-waru, that the governments there have realized that going back to find that traditional knowledge, re-engaging those populations, not only has the benefit of reconstituting the natural environment, but it gives people an opportunity to get back their culture in a way that it's positive all around.
Okay. Chris, here. You'll get your chance.
I'm just curious, there's been a lot of attention on the Arctic and the sea ice, the degradation of the sea ice. What about the Antarctic?
Yeah, that's a good question. I mean, the models, when they produced these predictions, they predicted that the Antarctic would warm equally to the Arctic. And in fact, that's not happening. The Antarctic is not warming at the same rate the Arctic is. And the reason for that is the Antarctic is covered by a glacier. And that glacier is absorbing a lot of that energy that's associated with it. The only place in the Antarctic that is warming at a rate that is equivalent to the Arctic is the Antarctic Peninsula. And the reason is that it's deglaciated. And so you have the feedback effects in that area that are warming it as well. And so mostly the climate signal is strongest in the Arctic. But the Antarctic researchers will tell you that they're seeing equivalent things on the Antarctic Peninsula And a lot of the glaciologists are starting to be quite convinced that the ocean is warming underneath the ice shelves in the Antarctic, and this is causing a lot of these ice shelves to break off. And you've probably heard about a number of these in the Antarctic with the with some of the Larsen B and these big ice shelves. We have ice shelves in the northern hemisphere as well, on the north end of Ellesmere Island, and a similar thing is happening with them. They're being affected by a warming ocean coming in underneath them and causing them to break up as well. So it's not just the sea ice, but it's also the glacial ice that is responding to these changes.
Do we have another question at the back?
With sea ice melting, do you think there will be natural resource exploration?
The simple answer to that is yes, and it's already started. Just to give you an idea of what's going on with resource exploration in the Arctic, Imperial Oil and Exxon are building a drill ship to do experimental drilling in the Beaufort Sea. This is where they're starting. And that drill ship will be used throughout the Arctic. And that drill ship is the size of a football field, and it is what we call a Polar 6 icebreaker. So it's a much more capable ice-breaking vessel than our ship is. And to move ice away from it, they're building 3 icebreakers that are all bigger than the icebreaker we have, because 35% of the world's fossil fuels that are undiscovered are in the Arctic Ocean. All of the countries that border on the Arctic Ocean are now putting a lot of energy into deciding who owns what part of the Arctic. And so when I talk to the public and to some of my classes, I tell them that there really is a gold rush going on in the Arctic right now, not just with hydrocarbon resources, but also with mineral resources. So there's a mountain, it's literally a mountain of iron in Baffin Island, on the north side of Baffin Island. It's called the Mary River Mine. And they are going to be developing that mountain of ore and will be shipping that ore out to Europe 24 hours a day, 7 days a week, 365 days a year, starting next year. And so there are proposals for 3 deep water ports in the Arctic. All of them are private sector related ports. And so the world is really looking at the Arctic as a new mineral and hydrocarbon non-renewable resource basket for the planet, not just for North America. China, for instance, is incredibly interested in what's going on in the Arctic because of their need for steel. So yes.
And before all of that development happens, they're going to have to do environmental impact assessments to find archaeological sites,
we hope.
among other things.
We hope. Yeah. We hope.
Okay, Digger wanted to ask a question.
My question is to Paul. As you were showing your models, and the one aspect which I think is being ignored is the post-harvest losses in many parts of the world, ranging from 20 to 30%. And when you take the food waste into consideration in the developed part of the world, the FAO report just released a couple months ago estimates that number is 30%. So when you take the post-harvest losses plus food waste into consideration, globally we are losing 30%. That should feed your 2.7 or 2.5 billion people if we can change our emphasis from the production to start preserving what we have produced.
Yep. Again, I agree with what you're saying. Part of the innovation I think that we need to do is exactly that, because it's a tragedy to have people that are short of food because of either distribution, storage, or waste. And there's certainly a lot that technology can do to try to address that. And whether that's sufficient to feed the 9.5 billion, I don't know, but it would certainly take us a good step that direction, I agree.
Okay, we'll take one more question. I see lots of hands, but we'll take this one over here.
Okay. My question actually is for Dr. Milne. Along the lines of fossil fuel consumption, the causes of carbonization of the atmosphere, is people using energy as a society. And one of the things we'll have to do, either through peak oil or through actual acts of preventing or attempting to prevent climate change, is transition away from our fossil fuel energy system. So within the history of people and societies and stuff like that, I'm not entirely certain of our track record of transitioning from high energy sources of civilization to even different energy level civilizations or low energy civilizations. Can you say anything on that, or?
Well, that is an excellent question. And certainly with complex civilizations in the past, let's use the Maya for an example. Over time developed an enormously successful stratified society with really quite complex political stratification, social stratification, and so forth, that was based to a large degree on a strong agricultural base. And as population grew, you started to see people that were competing for those finite resources. So eventually, people started to consolidate power over who had access, who owned the land, who had the rights for distribution for the food that was actually generated, and such that the population continued to grow in the one of the valleys near Copan. That people started to move out into more and more marginal areas up the valley walls because the best land on the bottom of the valley it was taken over. So eventually you started to see the total numbers of people outgrowing whatever the available resources were. So eventually there was fighting, there were political struggles, and the Mayan kingdoms, they collapsed. So in that sense, it would be really hard to go back in time to a traditional hunter-gatherer way of life once that kind of social stratification has been achieved. And archaeologically, you don't necessarily see great civilizations like that do collapse, and they do collapse. We can't be arrogant enough to think that it's not possible to repeat history. That it's very difficult in order to go back to that more kind of smaller footprint per se for human adaptation. It's not necessarily the most hopeful answer per se, but we have seen the rise and fall of complex civilizations the world over for thousands of years. So, and a lot of it has to do about who can consolidate the resources and distribute them effectively, and who can use those resources to get other people to do for them what they want. So.
Thank you. I realize there are many questions still left to be asked, but I want to be respectful of the time commitment, so I'm going to ask Digver to make summary comments.
Thank you, David. First of all, I want to welcome you all, and especially on such an environmentally challenging day you made in such large numbers to this visionary conversation. So I certainly thank you for that, but also request you that when you walk back to your cars, please walk carefully. It would be even more slippery by the time you leave. The one thing I think all speakers talked about is both the scientifically and anecdotally we can say that the climate change is happening, and that climate change is causing many issues, raising many issues. Certainly the seasonally ice-free Arctic is a possibility which could lead to the exploration issues and what impact that would have on the globalization itself raises questions. Certainly, the likelihood of impact of climate change on food production is an issue. There are some, as Paul mentioned, some studies which show that there's a possibility some positive effect, but there are also some negative effect. And there are more questions than answers to say what the climate change would do to the food production and to the feeding the world population. Certainly, the climate change is causing the severity, and the severity of the number and the severity of the events is increasing, and that certainly is happening, and that would certainly pose challenges in terms of the basically in the climates where the severity increases, the crop production issues would be there, or even the impact on the human life is quite significant. So it certainly would challenge as all of us as human beings on the planet, because the climate change would certainly test our ingenuity and innovative solutions which we would find. And I think what our innovative solutions would basically, we would be judged 5,000 years by archaeologists, whether we found intelligent solutions or not so intelligent solutions. And that's how we would be judged, how we take actions today. Thank you.
Thank you, Digvir, and I want to thank all of the panelists. Really appreciate the contributions. It's such a, I always think for me as president of the University of Manitoba, it's just such a privilege to be part of this community of scholars and to have the opportunity to work with colleagues such as the people who served on the panel tonight. And I want to invite you to come to another visionary conversation to be held on February the 15th in this room, same time, reception outside at 6:30. Too much, too little, two lakes, an expert panel for a discussion on water resource issues that impact the supply and quality of water, the environment, and the future of this very critical resource. I would say, for those of you who are planning to come, this is the fourth visionary conversation. The room has been full every night, and in spite of the inclement weather to which Digvir's already made reference, it's full tonight. I want to thank you for coming, and I would encourage you to come early next time and get a seat. Thank you very much.